Two, one. All right, let's go. The pre-recorded lecture for the 20th of February. All right, so last time we investigated orthogonality a little bit more closely. Then we proved something called the Gram-Schmidt process, worked through an example. Today we will upgrade orthogonality to orthonormality, and we'll look at the classic standard unit vectors. Okay. All right, so let's recall that a list of elements in Rn is announced to be orthogonal if the pairwise dot products for distinct indexed elements is equal to 0. All right. Now, note in this definition, we noted that you need J and K to be different. Obviously, if J and K are equal to each other, the dot product equaling 0 would be bad news, because then the vectors would all be equal to 0, so the only thing that we would declare to be orthogonal is the 0 vector, but we obviously don't want to live in that world. Okay, but that then kind of leaves the question of, like, well, what can be said about the dot products of Vj with Vj? We saw that specifically show up in the Gram-Schmidt process, so, hey, it'd be nice if that was equal to, like, well, it can't be 0, but what if it was 1? That would make the computation super easy, right? Because then you don't have to do those divisions. Hey, there's an idea. So we'll upgrade the definition to allow for this, so we say that a list of elements, and now I'm going to use U's instead of V's here, are orthonormal if they're orthogonal, and each one is what's called a unit vector. Oh, hey, foreshadowing. If their length is equal to 1. Alright, now note this is equivalent to asking the following. When you dot uj with uk, obviously when the indices are different, they zero out. But when they're equal, that would give you the norm squared. And since we want the norm to equal 1, well, then the norm squared would have to equal 1. Okay. Alright, so before moving on and talk about why orthonormal is better than orthogonal, I do want to further ruin the word orthogonal to you. So I learned orthogonal, the word, and I was like, oh yeah, perpendicular. Just a fancy way of saying perpendicular. Then I learned about orthonormal, and because my brain desires consistency, I then started pronouncing this word as orthogonal. And the only time a professor ever laid their hands on me, I said the word orthogonal out loud in professor's office hours, and he grabbed my wrist, and he looked me dead in the eye, and said, orthogonal! It was so funny. Yeah, it was a good moment. Anyway. So, now it's forever wrong in your head. You will now forever say orthogonal, because you need to say orthonormal. Alright. Okay, well, why is orthonormal the better thing than orthogonal? Okay. Obviously, it's got the same property. It's still orthogonal. We're perpendicular, but the lengths are 1, and what does that really grab us? And as we will see here, the lengths being 1 is going to give us a really neat property about their span. Specifically, if you have an orthonormal set, and if you belong in the span, well, we know going in that this is linearly independent. Everything is non-zero and orthogonal. So we know that there has to be unique representation. And furthermore, the unique scalars are these. Ooh, just the dot products. So if you had an orthonormal set and you wanted to know how you lived in the span, you only need to compute a bunch of dot products, right? Rather than solving a system of linear equations. This is what we had to have done before. Beautiful. Life is good. Alright, so since we're in the span, we know we're equal to some linear combo. And now I want to prove that the scalars are all what I claim them to be. Alright, well, let's fix a j. uj dotted with uk is always equal to 0 when j and k are different. And when we dot uj with uj, we get the norm squared, which we know has to equal 1. So when I dot product x with uj, the uj distributes and the scalars pull out. But all of these die off, other than the jth one. And when we get here, that dots to 1, and so then we get alpha j. Hey! Exciting. Alright, so there we see one of the reasons why orthonormal is the better thing. They allow for this very efficient span computation, and as we know, any linearly independent set can be turned into an orthogonal one where the orthogonal things in question are non-zero. And so we can then produce an orthonormal set by simply dividing the vectors by their norm. That would force them to be unit vectors. So the Graf-Schmidt process actually doesn't guarantee a orthogonal set that has the same span. It gets you an orthonormal one. So if you had a significantly complicated spanning set, maybe you want to Gram-Schmidt it to get an orthonormal one, which then has very efficiently computable spans. Ooh. Ooh, ooh, ooh. I wonder if that's going to be really nice when we start talking about projections a little later in the course. Alright, but talk is cheap. Let's actually go for the process of taking a linearly independent set, here's one we saw last time, and turning it into an orthonormal one with the same span. So, step 1, take the initial vector and divide out by its length. This just so happens to already be a length 1 vector, so nothing interesting happens. Now, we can compute the Gram-Schmidt process, but note here, I don't need to worry about a division. Right? Because I already know u1 dotted with u1 has to equal 1. Makes life a lot easier when you're doing this. Where it doesn't make life easier is in the next step, because the next step is I have to divide out by the length of v2 to create the u2, but the length of v2, square all of these and add them up, yeah, that gets you a square root of 2. Great. So while that makes the computation the next step easier, right, where I don't have to do any of these divisions, I now gotta do freaking arithmetic with square roots. But hey, conveniently cleaned up, so can't complain. However, you now immediately see that while you can do a orthonormal version of the Gram-Schmidt process, square roots are invariably going to come into play, so the computations are, by nature, just going to be more complicated, unfortunately. Right, and in the end, we get our third vector here, which, again, is going to have these lengths with square roots of 2. So, great. Good stuff. Alright, well, now we've seen it in action, and we saw kind of a bit of a caveat. While it does make this computation easier, because it drops out the divisions, the trade-off is that now you have to sort of work with square roots. And it usually is the case that they actually clean up nicely and work out, but you will end up with some nightmare situations where you have like a square root of 59 floating around. I've computed some nasty ones in my past. So, no guarantee, but it does make this part of the computation maybe a smidge easier. Alright, now that we know about orthonormal and how to Gram-Schmidt orthonormally, let's wrap things up today by talking about the standard unit vectors. Right, now what are these? So they're defined as follows. There are n of them in Rn, and their kth entry of the jth element on the list is 1 when these are the same and 0 otherwise. Okay, now you might be able to immediately see what these look like, but for a helpful visual, the standard unit vectors in R3 are these things. And there we kind of see what exactly these are. E1 has a 1 in the first component and 0s everywhere else. E2 has a 1 in the second component and 0s everywhere else. And E3 has a 1 in the third component and 0s everywhere else. So this is true as you go down the sizes. So if you look at the standard unit vectors in R, 4 billion, there's 4 billion of them, and each one has a 1 in the corresponding spot and 0s everywhere else. And, hey, note, if you smush these together, you get the identity matrix. Oh, isn't that interesting? Alright. Okay, note, these are clearly orthonormal. Right, these are all of length 1. Go ahead and compute that. Just take the sum of the squares and take the square root. You will get 1. And the dot products will always equal 0 for distinct entries because, right, the 1s won't match up and they'll just be paired with 0s. Okay, and furthermore, the following is also obvious as well. Every element of Rn can be written as a linear combo of these, where you just put the corresponding coordinate of x with the corresponding standard unit vector. So for an example of this, so you really kind of see what I'm saying here, let's look at the vector in R4, negative 1, root 2, e, and pi. Well, you can pull this apart into the standard unit vectors in R4, which, note, you see them on display here. where, right, in the first coordinate, you've got your -1. In the second coordinate, you got your √2. In the third coordinate, you've got your e. And in the fourth coordinate, you got your pi. Okay. So those are obvious. If you really want to sit down and write out the proofs of them, go ahead, but I'm not going to. This is clearly true. But let's conclude with a proof of something that we're going to exploit. Kind of already mentioned that, hey, when you smush the standard unit vectors, you get the identity matrix. And again, as I said, its name is going to come from the fact that there is a matrix multiplication that it acts as the identity for. And man, I wonder if that matrix multiplication is built off a dot product, which is why we've been spending, this whole week talking about it. Before we get to matrix operations, which is what we're going to do next week. Alright, so let's prove that if I take an element out of Rn, then dot prodding it with the standard basis element simply isolates the corresponding component. Now, you could directly prove this just by, explicitly looking at the dot product, but I want to prove it in a more interesting way. So, there are a lot of theorems in math that have multiple proofs, just how it goes. And sometimes there's the easy proof. There's the, just straightforward do the computation. And then there's these other proofs that on Math Stack Exchange and math memes and similar spaces on the internet where people do math for fun, like normal, well-adjusted human beings. There's this notion of nuking the mosquito, where you take out an easy math problem in a very overly complicated process. My analysis professor that I had, he was from New Zealand. He didn't call it nuking the mosquito. He called it using a bazooka on an ant. Right. He always stressed that for any of the homework problems, if you see an ant, you step on it. You don't take out a bazooka and shoot it. However, every so often, it's kind of fun to do that. So while you could directly do a computation here, I am going to I'm going to bazooka this thing. So, first we note that x is a linear combo of the unit standard unit vectors. We already know that. So note, it belongs to the span. Now, what do we also know about the standard unit vectors? They're orthonormal, orthonominal, as I typed here, Jesus. So what do we know? Well, by the earlier proof we did, we know that the linear combination that x would be equal to has the dot products as the coefficients. Now, since we're orthonormal, we know we're orthogonal, and we also know that we have to be non-zero, so we know that these are linearly independent. But what do we know about linearly independent things? We know that your representation as a linear combo is unique. We prove that, so it's got to be that these scalars all line up with each other. Beautiful proof, right? Using a bunch of previously established things. And as I said, in the words of Joe Dietzel, right? The math gods let you prove something, they want you to use them. So I wanted to use them today. All right, that ends the proof for today. That ends the content. So up next, we're going to start talking matrix operations. And as we'll see, matrices can be scaled and added in a natural way. But the real money is going to be multiplying matrices. And I bet it's got something to do with the dot product. Ooh. All right, so that's our next target, and yeah, see ya then.